Okay. Okay, yesterday we have proved product theorem, and for proving product theorem we were required to do a lemma where we have proved f of x is always going to be mod of f of x is always going to be less than mod of L plus 1. Okay, using that lemma we could prove product theorem. So the last in the series as far as algebra of limits is concerned, the last one is ratio. So essentially what we want to prove is basically f1 of x we want to prove f1 of x limit. Let me write down the final. No, what I wanted to bring it to your notice is if f1 upon f2 of x we want to prove is equal to L1 upon L2, it is good enough to prove reciprocal theorem first, and then reciprocal theorem and product theorem will give us ratio theorem. Reciprocal theorem and product theorem will give us ratio theorem. Okay, it is as simple as that. If we could prove that 1 upon f2 of x is equal to 1 upon L2, that will be our reciprocal theorem, and then 1 upon f2 of x can be considered as altogether a new function which is multiplied with f1 to get the ratio theorem. So down the reciprocal theorem first. So if we prove reciprocal theorem, it is 1 minute job to prove ratio theorem. In fact, we need not prove because reciprocal theorem is there with us and product theorem is with us, then ratio theorem is supposed to be proved. So reciprocal theorem, let is a subset of R, let F be from A to R, let C belongs to R, be a cluster point of A, let L belong to R, if 1 limit f of x as x tends to C is equal to L, and 2 L is not equal to 0, then 3 limit x tends to C 1 upon f of x is equal to 1 upon f. Okay, this is theorem. I wait for 5 minutes for you guys to figure out what would be the proof and what are the difficulties in writing this proof. So you get first-hand experience of the difficulties in going through this proof. Then we will figure out how to overcome those difficulties. So think about 5 to 7 minutes independently. Let us do rough work. What are we supposed to prove eventually? 1 upon f of x is equal to 1 upon L limit. So consider absolute value of 1 upon f of x minus 1 upon L. We want to show that this value is less than epsilon, whatever epsilon is given to us. Then this is equal to 1 upon f of x minus 1 upon L by definition. This is equal to L minus f of x upon absolute value of f of x into L. Okay, now you can split the absolute value in the numerator and in the denominator. Now this absolute value is less than whatever epsilon that we consider. We can write this, we can use this. I mean, statement number 1 will provide us with this absolute value sign, f of x minus L or L minus f of x. That is acceptable to us. But then we need to take care of this denominator. And the denominator is absolute value of f of x into absolute value of L, where absolute value of L is a constant and therefore we don't have any issue with this. However, absolute value of f of x, we are not sure what this is, because this is going to be dynamic quantity and it will depend on value of x, and therefore we, by our estimation method, we have to replace this quantity by some safe constant, and of course the inequality is going to be something like this has to be less than some epsilon upon mod L will be there, because it is there. You are supposed to replace this by some constant k, this fellow, and then when you are doing that change in the denominator, you need smaller value. What do we need here? So what is the requirement? K should be first positive. So let us write this as mod k. Mod k should be less than mod f of x. That is what we are required to find out. Can we find out a constant which is less than absolute value of f of x? If we could find out this constant, then we can directly replace it and we will not disturb the inequality. We don't want a bigger number, we want a smaller number because it is in the denominator. If we wanted the bigger number, then last lecture we have proved f of x, absolute value of f of x is less than 1 plus mod n. So we get a bigger number than mod f of x. Because it was in the numerator, we wanted to have a bigger number, bigger safe number to complete this proof. Now this f of x is in the denominator, therefore we want a smaller number than mod f of x, which is safe, to replace over there, and then whatever this constant e into k, mod k into mod, we will adjust it in such a way that eventually we will be able to show that this limit is less than epsilon, right? So therefore, before writing the proof of this theorem, basically what we need to write proof of is, can we really find out a constant which is less than mod f of x? Okay, so now for this, let us consider the diagram. What happens? We will do in general for f of x. So if f of x is some function, like yesterday we have said, this is f of x and this is your c, this is your L. Okay, now two cases, either this L is a positive number or L is a negative number. L can be, if your function is something like this, then at C you may end up having value of the function L which is negative, which is below x-axis. Okay, so if it is negative or positive, there is ambiguity, and because we are dealing with inequalities, we don't want that ambiguity. Therefore, we will consider, no matter what this f of x is, we will consider that function as mod of f of x. Then this function also will get reflected in x-axis and will get above x-axis to give all values positive. So even if this L is negative, we consider mod L, and this is the graph of mod f of x. Okay. Now you have C here, and we want to have, now suppose this is the case, then if any point here, if we could locate properly, of course it will be less than absolute value of f of x near C. बघा आता समजतंय का? So what we do is, whatever is epsilon given here, whatever is epsilon given, we can find out corresponding delta to be near C for every epsilon, because this limit is given. It is given to us that for any epsilon you will be able to find out delta. So for any epsilon, if we are able to find out delta, then consider a specific epsilon so that you are in the plus or minus epsilon limit from model, you will be able to find out corresponding delta. So this delta is going to be important in this proof also, because we will be eventually replacing mod f of x by mod k, right? And therefore this delta also need to be considered while choosing the final delta. Okay, so now what we do here is, suppose we take this value as mod L by 2. Okay, so now I straight away write down the proof of the lemma that we are required to do, and you go through it and tell me whether are you comfortable with it or not, and we will try to discuss that. Choose, which color should I choose now? Green. Red. Choose epsilon is equal to mod L by 2, which is greater than 0. That is what this point I am considering. Okay, epsilon. Then your statement which is given to you here, 1 implies, what does 1 tell you? That there exists a delta 1 greater than 0, such that for every x belonging to deleted delta 1 neighborhood of C intersection A. Okay, so now at the moment we will consider this as A. However, we have to discuss on this A, because there will be few points from A which need to be removed whenever we get value of L to be equal to 0. Okay, so we keep that thing pending. What is A star? Okay, intersection A star. Let me keep this as A star instead of A. For every x belonging to deleted delta 1 neighborhood of C intersection A star, we have, what do we write here? Mod of f of x minus L is less than epsilon, which is mod L by 2. Okay, this is our implication of statement number 1, which is given to us, and I am keeping this discussion little pending. Basically, we don't want those values of x which make function 0. So if we remove those values of x from the domain A which is given to us, we are safe. We will not be making L 0, and therefore we can take reciprocal of that. Okay, so A could be having some points where L will become 0, and because we are interested in 1 upon L, we have to ensure that all those x which make this function equal to 0 removed, and consider the domain as A star. The way we have done it, we had done it for definition of tan. We removed all the bad angles and created a set A where pi by 2 multiples of the angle are removed. That is what is the domain of definition of tan. Okay. So this result we get now, and now little bit of algebra will help us. बघा आता काय करते ते triangle inequality related algebra. So this is available with us. Now I am writing a statement: absolute value of L minus absolute value of f of x, difference of two sides is less than the third. Now, you may have several questions on this, but it is a triangle inequality. The way we have used earlier triangle inequality, sum of the two sides is greater than the third. This is difference of the two sides is less than the third. This is the triangle inequality I am using. Basically, I want to split these two guys and I have split them. However, it is a difference, therefore, it goes to the other side of inequality. So, you may spend little more time in understanding this step. That is fine. But this is correct. And therefore, what we get here is, if we compare this with this, we can say mod L minus mod L by 2 is strictly less than mod f of x. And that is what. But then, because mod L minus mod L by 2 is mod L by 2, this is mod L by 2 is less than mod f of x, and this is of course going to be greater than 0. So this is the important result that we have, because we were required to find out some constant which is smaller than positive but smaller than absolute value of f of x, and we got it. But then we got it for all those points where will this be true? It will be in the delta 1 neighborhood of C. This will be true. Okay. So now if you observe, let me reduce the size. So that everything is there on the board. Now, if you observe that this mod k which I was required to replace mod f of x in the denominator, I have got a number mod L by 2 which is positive and guaranteed to be less than mod f of x. It is a safe number to have, and therefore I will be replacing it by mod L by 2, making it mod L square by 2 as a constant in the denominator, and accordingly I will write the proof of your ratio theorem. So let me complete the proof of the ratio theorem also, and then we will discuss if required. Okay. So you can consider this as a lemma for proving the ratio theorem. And now let me write down the steps for this theorem. I was writing it in green. Proof: let epsilon greater than 0 be given. One and two imply there exists delta 2 greater than 0, such that for every x belonging to deleted delta 2 neighborhood of C, intersection A, let me write down again A star here, we have absolute value of f of x minus L is less than mod L square by 2 epsilon. Okay. So for writing the statement number 1, for making use of this statement number 1, I am how much epsilon I am considering? I am considering epsilon which is given multiplied by mod L by 2 mod L square by 2. That is what is the epsilon which I am considering now. I really do not know why that 2 has come there, but let us see later on. Okay. This is the first statement. It is utilization of given information. So this is delta 2. This is delta 1. Now I am going to choose delta which is minimum of delta 1 comma delta 2. Note delta is greater than 0. Okay. So now let x belong to deleted delta neighborhood of C intersection A star. For this x, both above statements are true. Consider this. Okay, up to this point we have reached now. So what are we going to do beyond this is erase this. Okay, then this is equal to mod x. Okay, this is equal to mod of L minus f of x upon mod f of x into mod L. Now the numerator is going to be less than, it is going to be eventually strict inequality because we are replacing many terms there. So this is less than what this has to be replaced by mod L square by 2 times epsilon divided by, this is what f of x we have already, mod f of x is less than mod L by 2, therefore this is mod L by 2 into mod L into mod L, which is equal to epsilon. Okay, so I think everything is there in front of you, and I do not expect that you do all these things independently because after lot of study, lot of hard work, people must have developed these proofs and they have written it. So we just cannot expect that all of us will start writing these proofs in third or fourth lecture of calculus, but we must understand it. Each and every step that we are writing must be understood properly. Now, instead of this A star business afterwards, you can always write that consider a set A star which is subset of R such that all those x which make this L equal to 0 are absent, or You create them and then maybe couple of lines you have to write what is A star, about what is A star. Maybe I will put those lines also now in this proof. You start writing. Let A star be the set such that all those X not A star is a subset of A. Okay, this lemma, basically this lemma gives you a constant, positive constant which is less than mod x. Yesterday's lemma gives you a positive constant which is greater than mod x, and therefore these two lemmas are important whenever it comes to estimation of mod f of x, whether in the numerator or denominator. You have to use appropriate lemma to get rid of that f of x or dependence on x, epsilon dependence on x. You have to remove it, and therefore for estimation these two lemmas are important. And when it comes to numerical problem, it is easy. I mean, it function is given to you, you can always figure out what should be the value of that constant. By considering some epsilon, you can find out. But when it comes to generalized f of x, we need to do something, and therefore we have taken extra efforts to get these two lemmas in place. Now, these lemmas will be useful for us whenever we want to replace mod f of x by either a smaller number, value of the function which is smaller, or the value of the function which is greater. So it is important. Mod L by 2 is a smaller number than mod f of x, and mod L plus 1 is a bigger number than mod f of x. These are the two important numbers that we need to have. So this is what is the proof of reciprocal theorem. Now, practically we are trying to adjust the constant in such a way that eventually we get this cancellation and we end up getting epsilon. Therefore, we can say by definition, theorem proved.
Sir, I think I have a different proof.
Sang.
Sir, let g of x is equal to 1 by f of x.
Hmm.
Then f of x into g of x is equal to 1.
Hmm.
Therefore, limit extends to c f of x g of x is equals to limit extends to c1 is equal to 1
नहीं, परत एकदा. Limit f of x into g of x
is equal to 1.
as x tends to c is equal to 1.
Therefore, limit extends to c f of x g of x is equal to limit extends to c 1 is equal to 1.
परत एकदा.
Sir, f of limit extends to c f of x g of x. F of x g of x we can replace it by 1. So limit extends to c1 is equal to 1.
आता मला एक सांग, तू जेव्हा लिमिट when you are considering function g of x is equal to 1 upon f of x, केलेस
Oh,
ना?
oh,
Consider function g of x is equal to 1 upon f of x.
oh.
How do you know the limit of g of x is going to be 1 upon L?
No, we don't know. We have to prove that.
Ah,
But f of x into g of x is equal to 1.
Hmm.
Therefore, limit x tends to c, f of x g of x is equal to limit x tends to c of 1 is equal to 1.
Hmm.
And by product rule, it is limit x tends to c f of x into limit x tends to c g of x.
Limit f of x tends to c.
Sir, he's saying that we should define another function h of x, which is a constant
Yes,
function.
yes, I understood. I'm just trying to check whether it is foolproof or not. Just a moment.
सर एक डाउट है.
एक मिनिट थांबा, एक मधमाशी आली आहे, मला चावीन ती. हा. हम्म. बोला. मग मी आधी रेकॉर्डिंग बंद करतो. ओके. So whatever we have done so far, what do we do so far? What have we done so far? Is we have defined limit, we have understood the requirement of limit, we have defined it, then we have said that let us deal with the algebra of limit. We proved addition theorem, we proved subtraction theorem, we proved product theorem, for which we required lemma, where we have proved mod f of x is less than mod n plus 1. Then we proved reciprocal theorem, where we required to use lemma, where we have proved mod L by 2 is less than mod f of x, and both are positive, and we proved reciprocal theorem, and hence we declare that the ratio theorem is also available. So basically we have done algebra of limits, and in one lecture we have also learned with numerical examples how to find out delta given some limit, given some function and its limit, and epsilon. If epsilon is given, how do we find out delta in terms of epsilon? We have learned that. So far in differential calculus, we have done this much. Now let us move and create few more definitions. Suppose you have a function like this, and you are at C, where the C is not in the, we so far what the approach that we have taken is we are not bothered about what happens at C. Okay, so whether this point is a part of the function or not, we are not worried about it, and our focus was on what happens in the neighborhood of C. We were thinking of finding out what happens in the neighborhood of C and what happens in the neighborhood of L. That is what our interest was. But now suppose if we say, no, now, okay, having understood, suppose this limit exists, limit f of x as x tends to C is equal to L. Suppose it exists. So the meaning of this statement is if you go to C from left hand side, if you go to C from right hand side near C, the value of the function will approach L, right? So when I am saying when you are going near C from left hand side, I should define that. So let us define definition. I want to define what do I mean by limit f of x as x tends from negative side, from left, is equal to L, and I want to define limit f of x tends to C plus, that is from positive side, is equal. So can we now create the definitions for these two limits? We have already created definition for this limit. What changes will you make in that definition so that we have a definition for this is called left hand limit, and this is called right hand limit. Now you should come out with precisely correct definition of left hand limit and right hand limit. I give you 5 minutes. So for left hand limit, the only change that you will do in the definition of the limit is, of course, where the limit was given, you have to write this first part, and for every epsilon greater than 0, there exists delta greater than 0, such that for every x belonging to open interval c minus delta to c intersection A, we have this, and for right hand limit open interval c to c plus delta, you have the same thing. That is what is the left hand limit. And okay, so left hand limit and right hand limit together is our old limit. Okay, when we say limit only, it means left hand as well as right hand, right? So it includes both. C is surrounded by both sides, and therefore left hand as well as right hand. Okay, so now the question is, so far in these definitions, we are not worried about what happens at C. Suppose C is a part of the domain and C is well behaved, and if suppose f of C is equal to L, I mean, what better can happen? Value of the function at C is also equal to L. That means there is nothing hollow, everything is filled. Right? So this is win-win, happy, happy, happy. I mean, 3 times happy situation. Left hand limit is L, right hand limit is L, and the value of the function at C is also equal to L. We say that function f is continuous. Okay, that is the intuitive meaning of what do we mean by continuity of the function. It has something to do with limit. We will write down formal definition of continuity also. But this is what is understanding. So you are complete this board. Then we will write formal definition of continuity. Then we will see how do we check continuity of a function. What are the tricks? Okay, so definition. Let A be subset of Now here deleted delta neighborhood will not be there because we want that C also. Neighborhood, delta neighborhood of C, intersection A. We have f of x, absolute value of f of x minus f of C. Instead of bringing that L, now we are using value of the function at C is less than epsilon. Okay, so two changes in the definition of continuity compared to that of limit. One change is here and another change is here. We don't have deleted delta neighborhood. These are the two changes, and of course because we are not using L, we don't have to define L. That is what is the definition of continuity. Function is continuous if limit exists and that limit is equal to value of the function at that point. Okay. Where is my page number? 13, 14. Okay. झालं इथपर्यंत लिहून सगळ्यांचं? Okay, now for all practical purposes, we can always do this. Limit x tends to C, f of x is equal to f of C. If this happens, then this particular symbol, I mean, it is this LHS taking care of left hand limit, right hand limit? Yes. And is RHS taking care of value of the function at C? Yes. Therefore, if you just cross check the limit as x tends to C, and if it is equal to the value of the function at C, then maybe this is the condition which we oftenly use to check continuity of the function. So the definition is in one place. Epsilon delta definition is in one place. Now, what is the practically commonly used trick to find out continuity? Check whether limit exists and the value of the function at limit is same as that of value of the function at C. If it happens, so left hand side takes care of left hand limit and right hand limit, and right hand side takes care of value of the function at C. And therefore, if you could check this limit, you can decide upon the continuity of the function. Okay, so let me ask you a few questions now. What question should I ask you? Suppose I have a domain A is equal to 0, 1 union 2, and I define function f of x from A to R, and let me define function also. Y is equal to f of x is equal to x, suppose. Okay, then is function f continuous at 2? Think about it. 2 point. Okay, so let C belong to A is the only statement that we want to make here in the definition of continuity, and just remove this to be the cluster point. It need not be cluster point. So that is what is the hint of that problem. So it was not required here. So there are one more than 2 changes. One change is f of C here. Second change, it is not deleted delta neighborhood. And third change is we are not worried whether it is a cluster point or not. It should belong to A because we are interested in value of the function at C. So earlier C was belonging to R, now C belongs to A. Okay. Okay, so now you can change your answer.
सर सी इज नॉट अ क्लस्टर पॉइंट फक्त कंटिन्युटीच्या डेफिनेशनसाठी का लिमिटच्या पण
सो कंटिन्युटीच्या डेफिनेशन मध्ये क्लस्टर पॉइंट मी लिहिलं होतं ते चुकलं, ते आता काढून टाकलंय. त्यामुळे इफ इट इज नॉट अ क्लस्टर पॉइंट, इट इज आयसोलेटेड पॉइंट, that is okay with the definition as far as definition of continuity is concerned. आणि आता लिमिट च्या डेफिनेशन मध्ये क्लस्टर पॉइंट आहे, पण लिमिट ऍट 2 हा विषय येऊच शकत नाही, कारण लिमिट जेव्हा विषय येतो तेव्हा त्याचा नेबरहुड मधलाच विचार करायचा आहे. whenever we talk about limit, we talk about neighborhood of C, and we never talk about value of the function at C whenever we talk limit. When we talk continuity, we talk limit as well as value of the function. Okay, now as far as isolated point is concerned, it is of course not the cluster point. Therefore, you do not have anybody to compare whether the continuity, and you don't have any points near to challenge the continuity at C, and therefore we don't have choice but to accept that the function is continuous at C, because there is nobody to challenge. Now this kind of situation has happened in our life earlier also many times. There is nobody to challenge. When convex function intersection of two convex functions is a convex, when intersection of two convex sets is a convex set, we proved this in 8th standard, and we said is point convex set. We had to accept yes, point is a convex set even if we do not have 2 points to join the segment and check whether that segment belongs to that set or not. We don't have anything, we have only 1 point. When 2 lines intersect, we have only 1 point. and therefore there is no second point to challenge the convexity of a point, and therefore finally we agreed that intersection of two convex sets is a convex set. Once more, this kind of situation was there with us to accept this reality, because there was nobody else to challenge in the neighborhood, in the nearby. In the, I think, set theory, is empty set a subset of every set? Of course, we have to accept the fact that empty set is a subset of every set, because there is nobody to challenge not being subset. There is nobody to challenge not being subset, because if I want to say A is not subset of B, then I must have an element in A which is not an element of B. But because empty set did not have any element, we had to accept that empty set is a subset of any set. Similarly, now here, as far as continuity of the function at isolated point is concerned, we wanted to check left hand limit, but it is not there, available is nahi hai. We wanted to check right hand limit, but it is not available. Okay, then we will check value of the function at C, and it is equal to C, f of C. That means the function. So the necessary condition, if everything is fine, if the point, basically if the point is an interior point, then left hand limit, right hand limit, and value of the function at C, all three conditions will be satisfied, and you can rest assured about the continuity when the point is interior point. When the point is boundary point, suppose now the function which I have given you just now, can you tell me, is the function continuous at 2, at 1? Is the function continuous at 1? 0 to 1 union 2, that is what is the limit given to you, I mean domain given to you. Again, the function is continuous at 1 because left hand limit is 1, value of the function at 1 is 1, and we don't have right hand limit because there are no points in the right hand side of 1.
No, but the function is not defined at 1. The function is not defined at 1.
Function is not defined at 1. Yes, just a moment. Now, so okay, at 1 we don't have value, so let me change that domain. Let me make that domain that is correct, because the value of the function at 0 is not defined because the point 1 is not there in the domain. So let me make it 0, 1. Okay. Now the question is the function continuous at 1? Is the function continuous at 1? Yes, function is continuous at 1. Why? Because left hand limit of the function at 1 is equal to value of the function at 1. Right hand limit, we don't have any point in the right hand limit to challenge discontinuity of the function at 1. So at 1 you have left hand limit and value of the function. Out of 3 conditions, you have 2, left hand limit and value of the function. Are they equal? Yes, then the function is continuous. If I ask you, is the function continuous at 0? Yes, it is continuous at 0. We don't have left hand limit, but we have right hand limit, and we have value of the function at 0 is equal to 0. Therefore, it is continuous. In every other point between 0 to 1, it is continuous. At 2, we don't have left hand limit, we don't have right hand limit, we have value of the function is equal to 2. Correct. Therefore, it is continuous. So, this.
But
Yes.
F2 ला सर epsilon is equal to 0.5 ठेवला तर मग डेल्टा एक्झिस्ट होणारच नाही.
नाही कळलं परत.
Sir, it is not deleted delta neighborhood, so it will still exist and it will have only 1.2.
There is nobody to challenge the continuity at isolated point. This is what you should understand. Continuity can be challenged by the points neighboring C, and there is nobody in the neighborhood of C. No matter what delta you choose, does not matter. C is an isolated point, and therefore you will be able to find out delta where there will not be anybody to challenge continuity.
Okay.
Therefore, left hand limit does not exist, right hand limit does not exist. It is not there. The points are not there. How will you find out? Those points are not there in the domain. You will not be able to find out left hand limit, right hand limit. And therefore, we don't have choice but to accept that the function is continuous at isolated point.
So can we not say that by definition also 2 is a continuous?
By definition?
Sir, f is continuous at 2.
Yes, I am saying that only. By definition only. By definition, f is continuous.
Because we are not taking deleted delta neighborhood, we are taking delta neighborhood.
Yes, and value of the function f of c is going to be 2 in this case. However, now I might say that I might write the function like this. Understand? F of x is equal to x if x belongs to 0 to 1. No, still it is going to be continuous. No, I have something else in mind which I will do later on. Correct? Okay, are you convinced about the continuity of the function at isolated point? That is very important because see, continuity at any general point or a cluster point is very easy to find out. What is going to be difficult to check or where majority of the students will make mistake if it is isolated point included in your domain. Normally, isolated points are not there in the domain. कोणी असं deliberately असा डोमेन तयार करत नाही की ज्याच्यामध्ये isolated points आहेत. पण suppose if I want to check the conceptual clarity of the students, I can suppose I make this problem like this. Let A be set of natural instead of this. Let A be इथे मी A च्या ऐवजी I can always write down say natural numbers. Let f be defined from natural numbers to real numbers. Let y is equal to f of x is equal to x. Okay, is the function continuous at 2? Is the function continuous at 2? Yes, it is continuous at 2. It is continuous at every integer. This is little anti-intuitive, but it is important. Maybe in physics you have been taught that function is continuous if you sketch without lifting the pen, then it is continuous. But yes, that is also correct. So it is basically correct in majority of the cases of the function. But suppose I define a function from natural number to real numbers and I say y is equal to x, then is function continuous at 2? Yes. Is function continuous at 5? Yes. Is function continuous at 500? Yes. Because there is nobody else to challenge the continuity. It is a discrete points which are there in the domain. And the value of the, so there our left hand limit, right hand limit, they both of them are not available, therefore I cannot check it. I will check value of the function at c. Is it equal to f of c? Yes, therefore it will pass the test.
सर पण मग आता आधीच्या A to R मध्ये का आपण फंक्शन कंटिन्यूअस नव्हतं?
A to R मध्ये फंक्शन कंटिन्युअस आहे ना 2 ला, काय प्रॉब्लेम आहे? तेच सांगतोय मी, आयसोलेटेड पॉइंटला कंटिन्युअस आहे. Anti-intuitive, therefore you have to take time to digest this. Okay. Now, if f of x is equal to 2, f is defined from R to R. F of x is equal to 2. Is it continuous at x is equal to 5? Is f of x continuous at x is equal to 5? Voila. Easy. अरे हाथ का? Yes or no? Is f of x continuous at x is equal to 5? Yes. Why? I mean, reason is limit f of x as x tends to 5 is equal to limit 5 as x tends to 5 is equal to 5. So left hand limit, right hand limit, done. And what is the value of function? F of 5 is also equal to 5. Therefore left hand limit, right hand limit and value of the function same. Therefore it is continuous at x is equal to 5. So with this I can conclude saying that all constant functions are continuous. Now see, so far we have discussed continuity at a point. Okay, now therefore function is continuous. Definition, actually this is function is continuous over domain of definition if it's continuous at every point in the domain. Okay, so I am saying all functions are continuous, all constant functions are continuous over R. So if domain is R and it is said that f of x is equal to constant, then they are supposed to be continuous over R. Then if I say f is defined from R to R and f of x is equal to x, is this continuous? Is this function continuous over R? Now we don't want to give this answer based on our intuition, but we should be able to write the proof. And the proof for this is what is left hand limit, what is right hand limit, and what is the value of the function at that point. Is left hand limit equal to right hand limit equal to value of the function at that point? If it is same, then we say that it is continuous. Okay, so if function is defined from R to R and if it is f of x is equal to x, then is it continuous over R? That means is it continuous over every point in real number set R? So you can take one real number C and prove that it is continuous at C and therefore it is continuous at every point in R and therefore it is continuous over R. Okay, so it is not very difficult, it is easy to prove. Okay, the proof will be let C belong to R, limit f of x as x tends to C is equal to limit x as x tends to C, which is equal to C. Why is this C? Because if you approach this x from left hand side of the C, right hand side of the C, the value of the function is f of x is equal to x, it will be exactly whatever value of x that you have will go here and that will be the value of the limit is equal to C. Okay, and value of the function. So limit, when you write this limit like this, which is equal to f of C, hence it is continuous at C and C is the general representative of any point in R, therefore it is continuous over R. Okay, so now therefore polynomial functions are very good functions, very friendly functions, because normally f is supposed to be p of x is a polynomial over real numbers. Then what is polynomial? Suppose linear polynomial, if I take a1x plus a0, p of x is equal to, then will p of x polynomial function, if it is defined from R to R, that is what this is. This means p of x belongs to R of x, means it is defined from R to R, and the function definition is like this, where a0 is a constant and a1 is a constant, and multiplied expression is like this. Now, because we have proved the algebra of limits, theorem related algebra of limits, now here in this above discussion, what we have proved is limit of a constant function is same number, limit of another constant function is the same number, and limit of f of x, which is x as x tends to C, is C. That is what we proved here. And then we are doing algebra of these three things. Limit a1. So what we are doing here is limit a1 as x tends to C is equal to a1. Limit a0 as x tends to C is equal to a0. And limit x as x tends to C is equal to C. These three things we have proved just now here. And now we are doing algebra of them. Therefore, limit p of x as x tends to C is equal to limit a1 x tends to C into limit x tends to C plus limit a0 x tends to C. Now we are allowed to write this because of the algebra of the limits that we have done. And the answers for this is going to be Finally, the answer A1. This is going to be C, and the answer here is going to be A0, which is going to be equal to Fp of C. And therefore, this linear polynomial is continuous over R, and therefore P of x belongs to R of x if defined like an x raised to n plus an minus 1 x raised to n minus 1 plus dot 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 plus a0 is continuous over R, and hence polynomial functions are very functions, they are continuous. लिहून घ्यायचं. Okay, understood. So can somebody tell me why when we do epsilon calculations, basically function minus value of the function after taking the limit, absolute value, and when we start simplifying it, why do we end up getting an absolute value of x minus c? Okay,
So-
in the meanwhile, wait, in the meanwhile, I have just started the recording. So this is a formal proof why f of x, limit f of x tends to 5 is equal to limit 2x x tends to 5 if f of x is equal to 2x is equal to 10. What is the proof of this? Why? How do we prove that this is correct? So we consider 2 epsilon greater than 0 be given, 2x minus 10, 2 comes out common, and this quantity should be less than delta. So 2 delta is equal to epsilon, therefore delta is equal to epsilon by 2. So if we take delta is equal to epsilon by 2, for every epsilon we will get the definition of the limit satisfied, and therefore this limit is 10, something like that. Okay. So basically the last question that I am asking is, if we start processing with f of x minus l absolute value, why we end up getting at least one term absolute value x minus c? So now you can answer. कोणाला उत्तर द्यायचंय? This particular discussion so far is very useful because we have declared polynomial functions are continuous functions. Okay. So now, before really using this continuity for some other functions and establishing some special limits which we are required to use eventually, maybe we do in remaining time today, let us write complete detailed proof. I will give you sufficient time to do that also. Write detailed complete proof of limit x tends to 2, x cube minus 8 upon x square minus 4 is equal to 3. Five 10 minutes you try to think why is this going to be true and how can we write the complete correct proof of this. First of all, check whether it is correct or not.